Fame is AB. That's the first line of a Dickinson poem. And then it goes, it has a song. Okay. There's a dash. It has a sting. And is that a comma? 2. It has a ring. Okay, so that is Dickinson. You've all heard of her. This is by Miss Dickinson. Okay, so fame is a B. It has a song. It has a sting. R2, this is OO. It has a ring. Now, this poem, according to me, works as is identical, similar to a definition. When mathematicians write definitions of things, this is what they do. Okay, they say it has this condition, it has this condition, and maybe this condition too. Then we can define fame to be a B. Okay, so this is the definition of. So if you think of this poem as an example of a mathematical definition, so what we are defining is that we're saying that fame F equals B. Just write that down. So we are saying that there's an equality between fame and B if and only if and only if. I know I'm changing the topic, but since this is how but we'll look at this poem once I do something else. If and only if it has, let's see, if fame has a song, has a sting, and a wing. If fame has a song, sting, and wing, then it is the same as a B. And maybe I messed this up because we could do B as a fame and then reverse it. But anyway, so this is an idea of a definition. And we'll be doing a bunch of definitions, more definitions, the theorems. This is a mathematical definition. This poem is an example of a poem that resembles a definition in mathematics. Okay, all right, so let's go back to what we were doing earlier. And I'm going to write a set here. We're back on this just to start the class. Okay, so we have a set, 3, 4, 5, 6. It's got 4 elements in it. It doesn't have a name. And we don't have to name it, but we could call it A. If I was going to give it a name, and let's say I call it D, I would put D here and equal to sign right there. Okay, so my question is this a subset of? This is a subset of the set of natural numbers. That's true, right? And set of natural numbers is a special set that has infinite numbers, and it starts at 1, 2, 3, and goes on forever. Okay? All right, so my question is this set bounded? Does it have bounds? Yes. What does that mean that it's bounded? It means it doesn't go on forever. Okay? So if I said, so let's ask this question. Does this, or is this set bounded? Is this set bounded? And the answer is yes, because it doesn't go on forever to the right and to the left. It does not does not go on forever to the right or left. Okay, so this is a set that has boundaries. It is bounded. We can say that. To the right, it is bounded by what? What is, why can we say that towards the right as we go, why can we say that it's bounded right here somewhere? Because it's bounded by 6, okay? And because 6 is larger than 3, 4, 5, we can say that this set is bounded by 6, and 6 is a upper bound, okay? So I'm going to call 6 a upper bound. So this is UPPER upper bound. Okay, now my next question is 6 the maximum element? Yes, so it's also the max of the set. So in other words, the largest element in this set can also be called the upper bound. Okay, that's pretty good. Now, it's also bounded from this side, right? Or my question to James is, what's the minimum here? Very good. So we're going to call this our min. And it is bounded on the left by 3 again. Okay. So if that is the upper bound, this is going to be called the lower bound. Okay. So right now, how many bounds, upper and lower bounds do we have? We have one upper bound and one lower bound. But in fact, there are other upper bounds and there are infinite upper bounds for this set because the definition of the upper bound is delete this. So this is if the letter M stands for an upper bound, right? An M can take any number, and then X is all elements X in this set, as in this set that doesn't have a name, okay? If all elements, X stands for all elements in X, and M is the upper bound, right now M is 6, and I can put any of these numbers in there, because X can be any of these numbers, because I have the equal to sign here, then it will still be true. So I stick 3 in. 3 is smaller than 6, smaller than the upper bound. Therefore, 6 is the upper bound. Let's get a number. Let's get a number from here that makes that false. Is there a number that will make that condition false? And the answer is no. If we did this, 6 is less than 6. Is this true? Because what that reads 6 is either less than 6 or equal to 6. And if one of those things are true, then this thing is true. So because every element of this set, when M equals 6, is true, therefore 6 is an upper bound. Okay. Now what we do is I'm like, okay, that's fine. 6 is definitely an upper bound, and the idea was that there are other upper bounds as well. So let's put in here the number 78. Because remember, this set is a subset of set of natural numbers. And I picked a number that is larger, or number to the right of this set. randomly 78. And I'm going to say, hey, 78 is an upper bound too. And how do we test that? By sticking 78 here and checking with all the elements of the set. Okay? Is 78 an upper bound? Yes, because this condition will always be true. When we replace M with 78 and X and try out each element of the set and stick it here, each time this relation will be true, this condition will be true. Okay, questions? Are we good? Okay, so 78 is a upper bound. So let's put, so how many upper bounds are there? 7 is an upper bound, 8 is an upper bound, 9 is an upper bound, 78 is an upper bound, 101 is an upper bound, all the way to infinity. They are all upper bounds of this set. What is the most useful and interesting upper bound? It's the smallest upper bound, the least of them, right? So we call this guy least upper bound. And this is the upper bound that is also inside the set. It's an element of the set as well. Okay, all of this will get slightly complicated in a second. So, as usual, this is the lower bound. And what's another name for least upper bound? So let's just get there. Unfortunately, another name for least upper bound, which is the leftmost of the upper bounds. And in this case, randomly, it's also an element of the set. That is not necessarily true all the time. The other name of the least upper bound is supremum. You're going to see supremum more often. S-U-P-R-E-M-U-M, supremum. You're going to see supremum more than least upper bound. And the shorthand for least upper bound is LUB. Okay, now this guy is the lower bound. Are there any other lower bounds? Is 0 a lower bound? If in the world, okay, so the question I have to go back to, imagine a world in which only natural numbers exist. And natural numbers are just this bunch, this special set called the set of natural numbers. We don't know, in our world, real numbers don't exist, rational numbers don't exist, integers don't exist. Only this set exists. So now, this is the lower bound. Are there other lower bounds? Yes. So is 0 a lower bound? And the answer would be not here. So this in context of the bigger set. The subset, the smaller set, if we were dealing with integers, 0 would work. Okay, how many people understand that, right? If this was a subset of the set Z, set of integers, then 0 would be a lower bound, minus 14 would be a lower bound. Okay, but in case we're just dealing with a set of natural numbers, so the lower bounds would be, so somebody give me a lower bound for this set, other than the one that's inside the set. Dodge 2, oh, wanted something else, but that's good. And anything else? Cheat sheet is right here. Very good, Dodge. You're not dodging the bullet today. What is 2? It's A, L, B, lower bound. What is 1? So when I say 1 is a lower bound, I'm saying that this set that contains 3, 4, 5, 6 is bounded from the below by the number 1. This set that contains 3, 4, 5, 6 is bounded from the below by 2. This set 3, 4, 5, 6 is bounded from the below by the number 3, which is also inside the set. 3 is the largest of the lower bounds. Is that true? So we call it, what do we call this little one? We call this greatest lower bound. And usually I should be just focusing on this today, but I'm just going to do this. And so this is GLB. GLB. Okay, all right. And let's just repeat here. This set that contains 3, 4, 5, 6, this is a set that's a subset of the set of natural numbers, and we're assuming in the world only natural numbers exist. 6 is an upper bound. 78 is an upper bound. There are infinite natural numbers larger than 6 or equal to 6 that are upper bounds. Everybody gets this. So this set is bounded from the above by 78. This set is bounded from the above by 6. 6 is also the smallest, least of the leftmost, the smallest upper bound, and so it's called least upper bound. We're interested in this thing. It's also called supremum. This is the lower bound we're interested in, which is the biggest or the greatest lower bound. It's called GLB. The other name that you're going to run into is infimum. Infimum. So when I see infimum, nothing. I definitely go towards the left side of the set. When I see supremum, I should go towards the right side. The numbers that are bigger, supremum to the numbers in the subset. The numbers that are infimum, inferior to the numbers in the set. Something like that might be able to. Okay, are we good? Let's move on. Questions? No questions? Okay. So if you look at the damn poem on the left, which I was calling an example of a definitional poem, it resembles this fame is a bee. Is this poem talking about bounds? Is there a bound somewhere? Yes. Okay, very good. And so it's bounded by these 3 conditions. We could say that. Also, if it has a wing, there's an upper limit to how far fame is going to spread. So there's that kind of idea in there. And that poem we were looking at, A Silken Tent, had that whole business of bondage and freedom. But it doesn't really work like this. This is kind of closer. This gives you the limit of how far the fame will spread, how far the wing will take the bee out from where the center is. Okay, it's not a very, it's a resemblance, but not a direct resemblance, but it's right there. Okay, let's move on, and we have to do this. So in order to get, I spent 37 minutes on this. No, we started at 11:15. Time to take a break. No, I have to get my fancy chalk now. I've got Japanese chalk, made in Korea. Yeah, made in Korea, but Japanese chalks. Okay, so let's do special sets. I'll use blue. No, I'll just use white. Okay, here we go. And I started doing it once. You unfortunately watched the video where the sound was bad. It's that stuff. Special sets. I'm going to go through really fast. First special set is set of natural numbers. 1, 2, 3. Forever to the right. Natural numbers has a lower bound. Everybody, does it have a lower bound? Does it have a minimum element? 1. Lower bound 1. Does it have a second lower bound? No. Because in this world, These are the only numbers. We have 1, 2, 3 forever. Okay. Does it have an upper bound? No. Infinity is not an actual number. So it goes on forever, forever, forever. No upper bound. Does it have a maximum number element? No. There's always, you find a maximum number, you'll find a larger one right to the right of it. Everybody's cool with that? Okay. Now what I do is, I'm going to put the natural number into, I want to draw a picture, and I'm going to stick the set of natural numbers into the real number line. The real number line is going to be in white, and real number line contains all numbers except for complex numbers. So real number line even contains all the numbers that we can think of. And what we're going to do is, on this real number line, we're going to stick in our set of natural numbers. So here is 1, 2, 3, and I'm going to put dot, dot, dot here. And I'm going to put n up here, the set of natural numbers. So what I just did is I took the subset. So I put the natural numbers on the real number lines. Okay, so between 1 and 2, how many natural numbers are there? Yeah, how many natural numbers? 0. Between 1 and 2, how many real numbers are there? Even if you don't know what real numbers are, infinite. Between 1 and 2, there are infinite number of real numbers. Let's pretend we know all these numbers. Between 1 and 2, there are infinite rational numbers. Okay? All right, good. Let's keep going. So now we're going to do Z, which is the set of integers, right? So you can write in your, if you're taking notes, integers. Somebody calling me? Oh, my friend Spam is calling me. So integers are -3, -2, -1, 0, 1, 2, 3. And again, I'm going to stick these guys into the real number, so I'll just do it quickly. This is 0, this is 1, this is 2, goes on forever. And this indicates that the numbers in the red are, you guys can see the red? Oh, fuck. So to change it to blue, or maybe yellow will pop up here. But you can't really see these numbers on the, and then this goes on forever on this side. Yellow is better slightly. Okay, now we go to rational numbers. And rational numbers are, how many fractions are there between 1 and 2? Infinite number of fractions. Rational numbers are fractions. So the only way we can do is describe that is to use that P of X notation. So all numbers in this set are M over N, such that M and N are integers, and N is not equal to 0. Is the number 2 a fraction? Yep, right? Because you can write 2 over 1. Now, I'll just tell you something. Square root of 2 is not a rational number, it's an irrational number. So, is this a rational number? And what part of the definition of rational numbers does that fraction break? The definition of rational number says that M, any number that we put in the numerator, better be an integer. Any number that we put in the denominator better be an integer. What have I done here? 1 is an integer, but square root of 2 is not an integer. In fact, it's an irrational number, and therefore, this is not a rational number. So this number does not belong to Q. Okay, and how do we represent rational numbers on the number line? Well, let's try yellow. We got 0 here. We're pretty good, right? And dot, 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 dot. Because 1 is a rational number, it's a fraction. 2 is a rational number, it's a fraction. Just to make sure we are making a point, I'm going to put half there. I've got an actual, I can put 3 over 2. That would be somewhere here. Is 0 a rational number? Yes, because 0 over 1 is a fraction. We good now? Now we come to the real number business. So how do we represent real numbers? Let's do the picture first. I forgot that. Here's a real number line. Every number on the real number line is a real number. So it's all in white. In fact, real numbers can be represented with something called the interval notation. This is another way to describe a set. And real numbers are numbers that go from minus infinity to plus infinity. Okay, so there'll be more on that, but we have to move on, and I'll look at the PowerPoint. There's the whole business of how there are gaps. So actually, let's do that first before we move on. Is everybody good with this? Let's move on. Okay, I love saying let's move on because, yeah, okay, 15 plus, we have 20 minutes. I like to teach for 3 hours straight. I have a student who will just sit with me for 3 hours. That's when you really have fun, but hey, we can't do that here. Okay, so I need my, oh yeah, I can just use this. I need my set, so I'm going to have, so let's do this before we do other things. So here is a number line. Okay, this is a number line, and I'm saying, hey, it's a number line that represents, I've got 1 here, I've got, no, 0, 1, 2. Where does square root of 2 is, remember, irrational? Square root of 2 goes right here because it's 1.41 something. So square root of 2 goes here. This is a irrational number. So this is 1. Square root of 2 goes right in the middle. This is a rational number. Okay, we've got 3 here, and I'm going to put the number pi right there. And number pi is a irrational number. So the set of a real number is made up of rational and irrational numbers. Okay? Why is pi an irrational number and not rational? Because if you put pi over 1, it doesn't satisfy the definition of rational numbers because this needs to be an integer, and it isn't. Because the set of integers only contains negative numbers, 0, and positive numbers, not a number like that. Rational numbers are the decimal numbers, okay? The decimal numbers that are repeating or are finite decimal points. Okay, so we got that. Now, let's say we live in a world. So we live in a world where we haven't discovered real numbers, and we've finally got through from integers, and we got to rational numbers, Q. And now I'm going to see, see how many of these numbers can be here. So I'm going to say on the left-hand side here, no gaps. Every possible number is on the real number line. Now I'm doing a second line called the rational number line. And in this line, I'm going to say that I'm just going to put rational numbers. So I'm going to put 1 here. And I want to put this guy here. It is there if this line was, but in fact, I have a circle there to indicate that square root of 2 does not is not there. That's a missing number in the set of rational numbers. Okay, 2 is there, 3 is there, but pi is also missing. So oh, sorry, thank you, very good. Because I'm too close to the blackboard. Okay, so there's right here, there's a hole here. There's a hole here in the rational number line. That's why we had to go to the real numbers. You cannot do mathematics, you cannot do calculus if all we had was rational numbers, because we wouldn't have square root of 2, we wouldn't have the number pi. If we never got to real numbers, and we were mathematicians who finally figured out that there's a larger set than integers and real natural numbers, that's called rational numbers. And we have to do all our math with rational numbers. So the situation I'm describing to you is back in Greece when they discovered rational numbers and they thought that was the limit of numbers. And then there was that triangle, there was the length that didn't add up, was actually an irrational number, the square root of 2, which is this thing here. If this length is 1 and this length is 1, Pythagoras says that you square this to find the length of this. What is this thing, this side called? Hypotenuse. So this is the leg, this is the leg. Hypotenuse, if you just know the length of this guy and they're both 1, then the length of the hypotenuse is that you square this length, you square this length, and then you take the square root, which gets you square root of 2, which is not a rational number. And all of a sudden they got stuck with, and they started committing suicide. It just fucking freaked them out completely. Okay. Because it was a cult of numbers. Yeah. All righty, folks. So here we have gaps. So we say that the real numbers have a property called completeness. Can't spell completeness. The axiom of completeness is satisfied by the real numbers. The rational numbers are not complete. Okay. Now, in the updated PowerPoint, I discuss all this quite well, kind of, because how do you show that a set is not complete? Is by seeing that if you have a subset on this number line, the lower bound exists or not. So what happens here is, if I took a subset of the real numbers, the least upper bound will always exist for the real number, a subset of a real numbers. And for the set of rational numbers, if I took a subset of the set of rational numbers, the least upper bound of that subset of rational numbers might exist and might not, because it could actually be one of these guys, which don't exist. And therefore, for a subset of rational numbers, the upper bound also has to be a rational number. Okay, so let's look at that. So all this is, it should be very clear by Monday. I'll go over it. And again, stop me. It takes sometimes a little while because I taught this and I didn't really understand any of this for 2 semesters. So you guys are very lucky. I actually now know how to present this thing in a way that I can understand and you guys can understand. So let's do the easy stuff again. Okay, here we go. I have a set. So let's look at a set. So let's call it A. And so this set is going to be a set that contains real numbers. And if a set contains, and it's going to be a okay, sorry. A is a subset of the reals, of the real numbers set. So A is a subset, and our set is going to be, let's just do -1, and okay, what if you have round brackets, not square? So I have round, that means, okay, let's just do this. I'm gonna stick this in here. So I have a set of real numbers that start start right after -1. So -1 is the lower bound, but it's not in the set. And square root of 2 is the upper bound, or and it is in the set because I have the square brackets right here. Okay. Or another way to say it is that the left endpoint is not included because I have a round bracket here. The right endpoint, so left endpoint is not included in the set. The left the left endpoint is not included, but the right one is in the set. Okay, now let's draw it. Here is the real number line, and I'm going to use these same things. So we have square root of 2 here, square bracket, and then we have -1 here. There's going to be 1 here, there's going to be 0, and bunch of numbers right there. So, okay, is -1 in this set? It is not. Is it the lower bound of this set? Yes. Okay, so this -1 is the LB, but it is not in the set. Is square root of 2 in the set? Right, very good. It is a upper bound. Is it the least upper bound? Is it the leftmost upper bound? Why? Because any number to the left of it will be smaller than square root of 2. Remember the definition? Square root 2 is our m. Does this have more upper bounds? Yes, it has. Pi is an upper bound as well. Is pi in the set? No. Okay. All right. So this number is what? LUB. So what I've just shown you is that just this example tells us that even if every time you get a subset of the real number, it will the LUB will be a real number and it will exist for that set. Now I'm going to do a set in which we're just dealing with rational numbers, and we'll find out that the LUB for a subset of the rational numbers does not exist. Okay, and I haven't written down the definition of LUB. We'll start doing that on Monday. So another way to write this set of rational numbers. So is this a set? Yes. Round brackets, square brackets, 2 endpoints. This is a set. Another way to say, and the name of this set is A, so I should actually put what? A here. This is in white because -1 is not included. The square bracket is in blue because it's, the number square root of 2 is in it. And then let's do this. Oh. Nice. Okay, folks, what goes to the right of x? I'm going to put less than and less than. There's something wrong right now, but let's start doing it. What should I put to the right here? Square root of 2 or root 2. Oh, I've never heard that in a while. And why is this wrong still? Equal to. So very good, because square root 2 is in the set. Russell? Russell? I'm just saying your name. Oh, okay. What about on this side? Very good. Data. Who knew you were a math fiend? If they would just teach mathematics the right way, everybody would be happy. We wouldn't be. And so this whole thing is called P of X. It's the condition. What this says is, right now, all numbers in the real number set can be in this subset. And then we say, at this point, any real number can be in the set. And we go, no, 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 just the numbers between this guy and this guy, including this one. Yes? Okay. All right, now let's go, because we definitely have run out of time. So here is now we are back in the world where if we get an LUB that is a, if we get an LUB of a subset of a rational number that is not a rational number, that means that rational numbers have gaps. Okay? All right, so you can have a subset of a rational number. And so let's just make, I'm just going to use this guy here. Okay, why is this set a subset of the rational number? Well, let's do this bit here, which I forgot to do. So I think I'm going to do it here. This is so terrible, you can barely see. So we have the set B equals, I'm going to do -1 here, and I'm going to put square root of 2 here. Okay, so, and can I say it's a set of rational numbers? Actually, why is this wrong? And actually, the slide is wrong too. You never use this notation. This interval notation is called, for sets is only used for real numbers. So, okay, so we have to do what? We have to do x, all elements x that will be elements of the set B better be rational numbers, such that x is not equal to a irrational number, is between, is smaller than this irrational number, but greater than -1. Okay? Now, excuse me, sorry. All right, is 3 a upper bound of this set B here? Yes. Is 3 a rational number? Yes. Is square root of 2 an upper bound of the set B? No, because square root of 2 is not a rational number. That is the only thing. It is, and is it, if you pretended it was an upper bound, show, and it is the smallest one. It is the least upper bound because it's the leftmost. There is no number in B that is bigger than square root of 2. So it fulfills the definition. The problem is it is not a rational number.